Guys, my name is Shreyas. I'm a educator at an academy. You can follow me on the Learning app as well. You can see my set of courses on the Learning app as well. This is a course about nuclear reactors part 2. So please do rate it, review it and share it, and please do subscribe our YouTube channel, that is the Unacademy Engineering Curriculum. Thank you. So guys, let's start with our course Elements of Mechanical Engineering. My introduction I've already given it. My name is Shreyas. I'm a BE Mechanical Engineering student. You can follow me on the above URL given, which is my Unacademy user platform. So nuclear power is the course which we'll be doing, and this will be the last lesson in the nuclear power course. So the target audience for this slide will be engineering students, general audience who are interested in science related topics, people who are interested in environmental resources, people who are interested in knowing the involvement of natural resources. So the learning outcomes of this slide will be, I'll be taking a lesson on the gas cooled reactors, a lesson on a liquid metal fast breeder reactors, a lesson on a heavy water reactors, as well as a lesson on a fusion power reactors, as well as the advantages of fusion power reactors. So nuclear reactors part 2 will be the lesson today. So let's start with the first set of slides. Before moving on to the lesson, let's have a quotation. It's not the situation, but it's the reaction to your situation that matters. So this quotation is solely about the willpower of a human being. So gas cooled reactors, let's start with the gas cooled reactors. The first gas cooled reactors which were founded were with the presence of carbon dioxide gas as coolant with a pressure of around 16 bar and graphite as a moderator. It was developed in Britain during 1956 to 1969. The fuel was a natural uranium which was clad with alloy of magnesium called the magnox. The graphite moderated helium cooled reactor is designed to use the U-233 as a fissile material and a thorium as the fertile material. Initially, the system would have to be fueled with the uranium-235 until sufficient uranium-233 is available for backup fuel. Because of very high melting point of graphite, these fuel elements can operate at very high temperature, and it is possible to generate steam at conditions equivalent to those in modern coal fire power plants. So this is how the gas cooled reactors are available and how they are there. This is an image representation or image depiction of a gas cooled reactors. So let's start with it again. So the basic fuel forms, they are the small spheres of fissile and fertile metal as carbides. The fissile spheres are of 0.35 to 0.5 mm in diameter, and fertile spheres are 0.6 to 0.7 mm in diameter. Each sphere is coated with 2 to 3 layers of carbon and silicon carbide to prevent fission products from escaping from the particles. Helium is a suitable coolant in that sense, as it is chemically inert and has good heat transfer characteristics and low neutron absorption. Being a monatomic gas, it can produce more power for given temperatures in the Brayton cycle as well as for higher efficiency. So let's move on to the direct cycle HTGR, that is nothing but the helium cooled graphite moderated reactor. So it is a gas turbine power plant which incorporates a regenerator and a multi-stage compression with intercooling. These cycles or these turbines consist of cycles such as pressure ratio, turbine inlet pressure which is around 50 bar, turbine inlet temperature which is around 900 degrees centigrade, and the compressor inlet temperature which is around 50 degrees centigrade. The temperatures at other points are shown in the computer numerical column and all. So with U-233 and thorium-232 as fuel, the gas cooled reactors, they function as a thermal breeder reactor. So this is what the gas cooled reactor is. You can see here the turbine generator condenser. So this is how it acts as a boiler also. you can see the gas blower and the fuel elements passing over here to the control rods. So let's move on to the liquid metal fast breeder reactor. So these fast breeder reactors are designed to create or breed new fissile materials while producing useful electric power. Most of them produce fissile plutonium from fertile uranium-238. The fuel rods in the core region thus contain a mixture of fissile plutonium-239 and uranium-238. The active core region, it is surrounded by a blanket of fertile uranium-238. This blanket region captures neutrons that would otherwise be lost through the leakage, thus producing additional fissile material. So, the doubling time is the time required to produce the fissionable nuclei, twice the number of the fissionable nuclei consumed. The high concentration of fissile fuel and the absence of moderator makes the core of a fast reactor smaller than a thermal reactor of the same power. With a high power density, thin fuel pins are used to minimize the temperature drop through the fuel. A coolant with excellent heat transfer properties is required to minimize the temperature drop from the fuel surface to the coolant, and also it must be non-moderating. This rules out water, and the best coolants for fast reactors are liquid metals such as sodium. Liquid metals have the additional advantage that their boiling points at atmospheric pressure are very high, so that most of them can be used as unpressurized in the reactor. Sodium is the most common used coolant for fast reactors. So you can see the liquid metal fast breeded reactor or the liquid metal fast breeder reactor over here. You can see the various apparatus which are used in this breeder reactor. So it consists of two primary loop, the breeder reactor, namely the pool type system, and the other namely the loop type system. In the pool type system, the reactor core, the primary pumps, and the intermediate heat exchangers, they are all placed in a large pool of liquid sodium contained in the reactor vessel or the reactor core. The liquid sodium is discharged from the intermediate heat exchanger to the pool. It is then pumped upwards to the core and it re-enters the heat exchanger. In the loop system, the intermediate heat exchanger is located outside the reactor vessel. So this is how the breeder reactor will be there. You can see the control rods, there are two types of control rods, namely one is placed outside the reactor and another is placed inside the reactor. So let's move on to heavy water reactors. They are very low neutron capture cross section of heavy water, makes it an excellent moderator and coolant, and permits the use of natural uranium up to 0.7% of U-235 as fuel. Reactors of this type have good neutron economy and they result in good breeding ratios as well as high fuel burnup and a reduction in fuel cost. The disadvantages of heavy water are it's very high cost, and like water, it's critical temperature limitation. So you can see the image representation of a heavy water reactor over here. So heavy water reactors, heavy water, moderated and cooled reactors have been extensively developed in Canada, and they form the basis of the nuclear power program in that country. They are called CANDU-PHW, which means Canadian Deuterium Uranium Pressurized Heavy Water Reactors. These reactors, they have several features that distinguish them from the other types. The moderator is contained in a cylindrical steel vessel called the calandria with a large number of circuloid tubes through it parallel to its axis, which is very horizontal. The active core region is approximately 6 meter high with a diameter of 7 to 8 meter. The D2O coolant enters the regular array of pressure tubes at 260 degrees centigrade and 110 bar, and it flows through the fuel elements, which leaves the pressure tubes at 320 degrees centigrade, and the net efficiency will be about 29%. Like the pressurized water reactor, there is no bulk boiling of coolant in heavy water reactors. So the heavy water reactors, they have a heavy water coolant pressure. in the reactor, which is about 88.3 bar, and the inlet and the outlet temperatures are around 250 degrees centigrade to 290 degrees centigrade respectively. In the heat exchangers, the steam is generated at 41 bar pressure, 251 degrees centigrade. The thermal power of each reactor is 1744 megawatt, and the electrical output is 515 megawatt, which gives a thermal efficiency of around 29.5%. So you can see the housing of a heavy water reactor over here. You can see the housing which is present here. So let's move on to our last reactor, namely the fusion power reactors. The fusion of light nuclei to form a heavy nuclei releases energy. To cause fusion, it is necessary to accelerate the positive charge nuclei to high kinetic energy in order to overcome electro-repulsive forces by raising their temperatures to hundreds of millions of degrees, resulting in a plasma. The plasma must be prevented from contacting the walls of the container and must be confined for about 1/10 of a second, having a density of around 10 power 15 ions per centimeter square. So the fusion power reactors, they are dependent on the deuterium and the tritium or the tritium. Deuterium, it being a very stable heavy isotope of hydrogen, is present in natural water, is the main fuel for a fusion reactor. It has self-sustaining temperature, which is a temperature of around 15 to 10 power 6 Kelvin, which releases around 17.6 mega electron volt per reactions. The first two D2D reactions occur at 500 to 10 power 6 Kelvin and release energy which is around 3.2 to 4.0 mega electron volt, and the fourth reaction releases very high energy 18.3 mega electron volt, but it requires a very high temperature, that is 1000 into 10 power 6 Kelvin for fusion. The tritium, it does not occur abundantly in nature, however it can be produced for a lithium breeding bracket that surrounds the plasma of the fusion reactor. So you can see the fusion reactor over here. You can see this is the plasma which I was talking about in the last slide. So the fusion power reactors, they actually have this plasma contained inside an evacuated tube of about 4 meters. The surrounding vacuum wall is through which it is there is around 14 mega electron volts. Neutrons from the plasma pass is maintained about 750 degrees centigrade, and outside this wall are two concentric regions, the lithium breeding moderator and the magnetic shield. The tritium is manufactured in the lithium bracket, and large cryogenic superconducting magnets of around 7 to 8 meter diameter maintain the magnetic shield. The binary vapor power cycle, they consist of a potassium topping cycle as well as a conventional steam cycle. It includes a tritium recovery system. So the advantages, so this is an overview of the animation drawing of a fusion power reactor. So the advantages of the fusion power plant are, it helps in the supply of deuterium when it is almost inexhaustible. The radioactive wastes are not produced in this fusion power reactor. It is very safe to operate. It has a high energy conversion efficiency of around nearly 60%, which can be achieved by the usage of fusion power reactor. The low heat rejection to the environment also takes place per kilowatt of the electricity generated. It is almost certain that large practical fusion power plants will be built in the 21st century. Once this technology is developed, an almost unlimited supply of energy will be available for the world's need, which is ushering in a better living standard for the human kinds to live all over the world. So thank you guys. Any questions, please drop those in the comments box below. You can find me at my Unacademy user platform mentioned over here. And if you have liked this presentation, please do rate the course, review the course, and please do recommend this lesson or presentation if you have liked it. And you can follow me on this URL, which is my Unacademy user platform. Thank you guys for your time. Have a good day.